Just go over the sort of stuff that's going on tonight, just in case you're not aware. Discussion tables, sort of birds of a feather sessions are taking place at 6 o'clock, 6 to 7, in the Seaport Ballroom. For those of you that are members of the security twits, the Twitter reception is from 6 to 8. And then immediately after that is the IO Active Party across the street at the Atlantic Beer Garden from 8 to 11. So plenty of activities tonight. So our final speaker today is Erik Cabetas, who's going to be discussing vulnerabilities in interpreted languages. So I have no bio on Erik, and I have no idea, where he's from because it doesn't say in here. And there's a picture of a Japanese domo character as him. So this is what he really looks like, and he'll talk to you about interpreted languages now.
Thanks, Chris. All right, so the quick bio is I've been doing InfoSec for like 7 years or so, and I can't even log into my computer. But I used to do a lot of research and testing and pen testing and also web application assessments, but yeah, great. It's like all right. Did everyone like gasp right there? So yeah, I used to do a lot of that stuff. Now I just kind of do it as a hobby, but still fun, right? So it'll always be fun. When you love this stuff, you always come back to it. It's fun. So what this talk will be about is just a high-level overview of interpreted languages and some problems that we've been seeing in the last 2 years with them. Also, I want to discuss points of interest where I think people haven't been researching enough and finding bugs. So now it's kind of like old hat. I'm getting to the point where I should be learning Python and things like that. But I really hope that this is kind of an inspirational talk for any of you guys that write fuzzers or do research in interpreted languages. Has anyone here found an interpreted language bug, security bug, or written a fuzzer for one besides Dino? Oh, which one did you find? Publicly? Yeah. Which one? What? Yeah. Not so much. All right. So Dino was saying QuickTime for Java, right? I say that that's a flaw in the library for QuickTime for Java, but not so much in the interpreted language. Oh. Yeah. So now let's discuss what we mean by interpreted languages. But before, I want to just mention Gregory D. Evans. For those of you who don't know, Gregory D. Evans is the #1 hacker in the entire world. And everything that we do, everything that all of us does every day is because of Gregory D. Evans. We have to thank him. He also knows Reggie Jackson, and he hires 13-year-old ex-felons for his security consulting company. Okay, so interpreted languages. Maybe we'll watch a video of his when we're done, if there's enough room. Tyler really wants to see it. Yeah. I just want to speak a little bit more about awareness. There's a couple folks doing very technical, specific presentations about interpreted language bugs. Don Bresnitsky and Justin Ferguson at Black Hat Japan and PH Neutral in 05 and 08. They did specific talks on interpreted language bugs, and Dom focused on Ruby, I believe, and Justin focused on Python. So we've seen a couple folks do very specific talks, but I'm trying to generalize a little bit of this stuff and talk in general about interpreted languages. So what do we mean when we say an interpreted language? So by my definition for our purposes here, it's at any point where you start out with a high-level source code language, and the source code goes through a language-specific JIT or just-in-time compiler. And then it gets turned into an intermediate representation. And usually this is known as a bytecode within the context of whatever interpreted language. And then it goes through some optimization steps and maybe some intermediate forms like abstract syntax trees or ASTs. And then at some point, you get the bytecode emitted, and that gets passed to an interpreter. And the interpreter is, we'll just call a virtual machine. And it will go through that and convert that intermediate language into actual machine execution code. And then you have your native executable code and stuff executes, right? So a picture of said process is source code in. It goes through lexical, syntax, and semantic analyzers. You have the intermediate code generator, and it emits some sort of intermediate representation, goes through your VM, and the VM may pull functionality from external libraries, such as QuickTime libraries, and then you get actual execution results. If any of you guys have looked at the SpiderMonkey engine, which is the JavaScript interpreter in the old JavaScript interpreter in Firefox, this is represented by the following source codes. So it does a scan, then it parses, it does emit, and then it goes into the interpreter. So, like graphically flows into what it does programmatically. So what are we not talking about? So we're not talking about precompiled languages, your C's, your C++, and for everyone that still codes in PCL and assembly. Nor are we talking about your pre-compiled or pre-runtime compiled intermediate languages like your Javas, your .NETs, and things like that that are pre-compiled into an intermediate language, and then at runtime the intermediate language is evaluated. And we're also out of scope is vulnerabilities in language frameworks. So just kind of anything like Spring or struts. So we're talking about these particular things. And these are modern interpreted languages by what I'm covering here. So your Ruby, your Perl, your PHP, Python, SQL and its variants, as well as JavaScript and VBScript, which many people don't pay attention to anymore, and regular expressions. So the couple things on here that people don't think about when they think popular interpreted languages is SQL and regular expressions. Like most people don't think, hey, a regular expression is interpreted language, but it can be an interpreted language or a compiled language. So if you guys have ever used regexes, you can pre-compile them. Some languages have bindings to pre-compile the regex and then actually run the regex over a buffer. And then SQL, that's usually the last one on people's mind. They think of SQL, they know structured query language is how I access data, but they don't think of it as an entire programming language or anything of that nature. So with all these things, there's hundreds of thousands of lines of C code behind them. And to get that whole process of source code in, execution out, it can get pretty complex, especially the easier the language is to use as an end programmer. So for instance, in PHP has a ton of framework within the language to make it possible to get in and start programming with little to no knowledge of traditional programming techniques. So PHP has a whole bunch of lines of source code as well as the rest of these languages. And even PCRE, which most people would think wouldn't be that complex, is still over 28,000 lines of code, or 27. So if you were to go by, I think Whitey's Venema said the famous phrase, in my code that I've written, I expect one security flaw in every 1,000 lines of code. And he was a self-proclaimed security expert, right? So if a self-proclaimed security expert wrote this stuff, he would have 780 security vulnerabilities in PHP, right? So the folks that do write this, they're very good developers for the most part, usually, but they're not security experts, and usually these languages don't have defensive coding techniques in place. I'm sorry, the developers of these language runtimes and interpreters. So the first one I want to discuss is PCRE, or Perl Compatible Regular Expressions. So the main PCRE library is distributed from pcre.org. And it's basically just a library for regular expression parsing and execution. And it's used all over the place in open source and closed source software. So, big names, Apache, glibc, PHP, and a lot of people don't even know, but Nmap has a regular expression engine within it. And now it even has a Lua engine, and I don't really think it should be called a network mapper. It's more the network mapping engine. It's got multiple script interpreters built into it now. The two widely publicized flaws in PCRE were in 05 and 08, and they both were variants of an integer overflow in the way that it handled quantifiers. So it would you give it a really big number, negative. If you got just the number right, internally it would allocate a heap buffer that was a little too small and copy your data to it. Now, that is publicly what was divulged. Now, if you actually go and look at the change logs of the source code, you'll find that there's a lot more than what they talk about, right? So if you're using PCRE and you just think there were those 2 bugs that were publicly made and they had CVE numbers for, there's more than that. And this is very typical of how a lot of open source and closed source vendors operate. They'll fix little overflows here and there in their release as just a matter of course, and maybe somebody notices it, but they don't really notify the public. They don't say you have to upgrade now because we fixed a buffer overflow and we think it's an issue. They don't mention that stuff. They just fix the overflows, silent fixes. They're not totally silent fixes because they did comment in the changelog, but there's no public notification of this stuff. So with PCRE, I think we see a fair history of buffer overflows and non-defensive coding practices. They just sometimes happen to find this stuff in just their everyday coding. And as far as I can tell, the 2 publicly reported ones were found by researchers, and these over here were just found by the developers of PCRE just in the course of their work. So one thing I want to say about all this is like a prognostication that there will be more bugs, because the history will repeat itself of this stuff unless there's a major change in their SDLC in the way that they code, and there's not. So within the history that we see here, as well as I hope folks go out and find more bugs, because the more bugs we find in these low-level, commonly used libraries, then overall for everyone, kind of security increases. So there will be more bugs in PCRE. Now, how could you use these bugs? Or like in the real world, PCRE bugs, what are they used for? So Charlie Miller, who is a Mac hacker extraordinaire, maybe Dino is as well, but so Charlie Miller used one of these PCRE vulnerabilities to win the CanSec West Pwn to Own contest last year. And basically all he did was realize that this PCRE library version that they used in Safari was an older version. And there are vulnerabilities in there that were not patched. So something that we see again and again is folks that bring in open source libraries or open source projects into their main development branch, and then they don't go back and check for upstream patches. They just bring it in, and maybe every 6 months or every year they'll update it. But it's not like a regular release, like PCRE released, we have to release. And that's just because, WebKit, which is the underlying engine for Safari that handles all the HTML rendering and JavaScript and things like that, WebKit has their release cycle. And as much as they're an open source project, they're also kind of pushed by Apple, as far as I understand. So they have their release cycle, and it's not always necessarily at the same sync as PCRE or the other components that they have. So paying attention to these type of bugs can win you a laptop, and I believe $10,000 is the purse for the CanSec West Pwn to Own contest. So the next language we'll talk about is Ruby. So Ruby seems to be the hot language nowadays, with Ruby on Rails being a really common framework for getting fast websites together. But the Ruby language itself was audited by a guy named Drew Yao from Apple. And in 2008, he found a lot of really cool bugs. And some of these were in the Ruby framework itself, and some were in the language. So he also found bugs in like WebBrick, which is the Ruby web server that comes with it. So that's what I mean when I say like the Ruby language framework. It's just kind of things that are associated with the language. But then he also found things within the language itself. So in some of the native types within the language had problems within them. The first one up there had to do with the way that string buffers were copied and appended together. The next three had to do with the way arrays were accessed and that you could store items within arrays. And the final one had to do with the way strings were formatted. So the first two there in red, those are ones that I think were a little more accessible to be exploited, in terms of you just had to have the code constructs for these to be vulnerable were a little more common than the bottom three. But in general, all 5 of these are going to be very, very hard to exploit if you have a proprietary proprietary source code. So, as far as the risk to a business, like when you see let's say you have a Ruby on Rails application and you see all these internal Ruby language bugs come out. So you think, do I need to worry about this? So for these internal language bugs, you have to have the source code laid out in a very specific manner. So you have to index into an array at this particular negative offset, or you have to have a for loop with strings appended in just a particular manner. So if you have proprietary source code on your web application, chances are that A, you'll have that exact same code construct, and B, that somebody will be able to figure that out blindly over the internet. The chances are slim to none. So I wouldn't even consider it any sort of risk that people that use Ruby or develop Ruby web apps need to worry about. Sorry, where was I going? All right. But what if you could look for code constructs that were vulnerable? So if you knew, I'm looking for a for loop, and then after the for loop, I'm looking for a plus equals string append, and I want to, across all applications on the internet, all open source applications, I want to try and find that particular pattern. So you can use different things like Google Code Search to set up regular expressions and look for those types of patterns in all the Ruby code that Google Code Search has access to. Yeah, question?
If you overflow the expression in Google Search.
I love this guy so much. So yes, Google Code Search uses PCRE. Do what you will with that. If they have an updated version, I don't know, but do whatever you want with that. So yeah, you can use Google Code Search, or you can abuse Google Code Search. I haven't done it. I don't know. You guys play around with that one. But I like the way you're thinking. Yes. So that's an interesting way to think about like trying to find these things. So, and that just goes in general. Whenever I find a new bug class, I always try and generalize it within a regex and throw it in Google Code Search and see how many dozens or hundreds or thousands of apps I find that are vulnerable to it. So that's a fun little trick you guys can use. So one thing I'll obviously say with this is there will be more bugs. So Drew Yao is pretty good, and Apple gives him a little bit of time to do auditing on this stuff. But he is not marked out. The second marked out takes a look at Ruby, it's gone, right? Or some of you guys in this room, I really hope. One person spending a little bit of time found 5 exploitable bugs. Now, when are the cases when these bugs are exploitable, or the ones in red that I mentioned? It's when you have an open source code construct that you can find, and then you say, oh, okay, so this Ruby on Rails open source app that a whole bunch of people use has that string append buffer loop that I'm looking for. So I can write an exploit, a remote exploit for this open source application. It's very, very target specific. So you would have to have the code construct in the open source application, and you'd have to know that somebody's running that in the exact version of the Ruby interpreter they're using. So you could write remote exploits for it, but it'd be very difficult. And I think on the Matasano blog, there are like 100 posts discussing the feasibility of this, how exploitable it was or not. So one thing I'll say about all these Ruby issues is that Drew wasn't the first to find all these. Although he was the first to get the CVEs and his name on them, from the Matasano blog, we see 2 posts by the guys I mentioned in the first slide, Dom Brzezinski and JF, or Justin Ferguson. So Dom states, wait, these are not new things. I spoke about these in 2005, these exact same issues. He didn't go and put advisories out. He didn't go and work with CERT. He just, at Black Hat Japan, he put them in his presentation and said, here's a bunch of 0 days. Like, here's what I found. Here's how I found them in Ruby. And they were very specific to Ruby. And since 2005, they've been sitting there. Nobody reported them. Nobody did anything with them. So two things come about from that. I wonder how many talks at security conferences people actually go back and like report vulnerabilities that are released in these talks. And the second thing to think about is that these things were publicly discussed in 2005, but they weren't fixed until the end of 2008. So if you were at Dom's talk, you for 3.5 years knew about these things, and you could go and audit and use the techniques Dom mentioned to write exploits for these guys. So then JF responds, awesome, but just wait until I go public with my JavaScript stuff. So I spoke with JF over email, and he said that he had a bunch of stuff in JavaScript that he was going to release at the end of 2008, but he never released it. I don't know why. So another thing Dom says is Yao had to rediscover the problems to make something happen. Way to go, Ruby core. All right, next language we'll speak about is Python. So just like Drew on Apple Product Security, we have Dave Ramal, who found a bunch of integer overflows in the native types of Python and some of the core objects in the language. So string object, Unicode, et cetera, all had a bunch of integer overflows in the way that they were instantiated and referenced. And also the interesting one from the security perspective is hashlib, which if you could exploit this, it could cause incorrect cryptographic sums to be produced, which might be some design flaw that you could produce somewhere else. If I can get this code to make an incorrect hash, maybe I could trick the design of it to let me through some security barrier. And then Justin Ferguson, he found multiple buffer overflows in the Unicode string processing, but it only affected 32-bit systems, right? So let's think about that statement. He found that if your app took in Unicode, which a lot of apps take in Unicode, and you ran it on a 32-bit system, which a lot of us have 32-bit systems, you were vulnerable to these buffer overflows. So these were actually remotely exploitable in the native string object that handled Unicode. So all your app had to do to be vulnerable is take in a string. That's it. So this is one that's a little more exploitable than the Ruby ones we were talking about, right? So it just had to take in a malformed Unicode string that could understand how to trick the internal object. So something that Google does as well is give their folks time to audit these types of code. So I got to say that's a really cool effort by Google's security team and Apple's security teams to give their employees time on the record to find bugs in their primary languages that they use, Python and Ruby. So these guys are 3 or 4 folks focusing on a little bit of their time on trying to find bugs. If just 3 or 4 of you guys spent a little bit of time finding these bugs, you could find buffer overflows in them, and it's not that big of a deal. So with Python, though, so I mentioned the Unicode one, where all you had to do was take a Unicode string to be vulnerable. But for some of these other ones, like the string object, the Unicode object, the long object, you have to give very specific code constructs to be vulnerable. So chances are that there's no way in practical code that you're going to see these be set up just the right way to be vulnerable, because you have to write code that just doesn't make sense. It's not useful for standard programming. So if we wanted to exploit this remotely, we would have to have some way to submit code, and it would have to be in exactly the same way or the exact way that we needed to exercise these bugs within the interpreter. So we would need something that just took our Python code and executed it. So Google has this really cool thing called App Engine, which takes your Python code and executes it. And when the App Engine first came out, I really wanted a login to it, because they were only giving out a small amount of logins for beta developers. But unfortunately, I was not one of those. And I sat there and I was like, oh man, I so wanted to get in on that because it could find some cool bugs. But luckily enough, one of the developers that did have a login made this cool app called Shell. So with shell, you just put in any Python code that you wanted, and it would execute it. So thankfully enough, once shell was made, I didn't have to have a login anymore. I just started playing around with shell app engine. Now, in the original version of the shell, the Python shell, they had so they have a sandbox, right? So it's not just a straight Python interpreter. It's this the same standard Python 2.5 interpreter, but with a lot of lockdowns. So it won't let you call any file system object. So it has a lot of corrooting and things of that nature. So you can't just go cavorting around the system and doing anything you want. So they had to sit there and think about every method, every object, and what is bad, what should we not let people instantiate. I played around on there, and I found a way to get through to where they stored the actual runtime. So here you see some of the Python code, which was their sandbox itself. So I could dump the sandbox and take a look at their PYC files and stuff like that. So my point of all this is, if you ever had a hosting environment or something like this where Python code was being run, then you could take care of some of these interpreted language bugs and get machine execution and break out of sandboxes and things of that nature. So, question?
If you posed as a legitimate developer, you could introduce a non-obvious source code backdoor by committing to the project's repository.
Sure. You could also do that with commercial companies. Join them and backdoor them. I would not suggest either or method. So his method is join join an open source project and just stick backdoors in there. So yes, that is a security vulnerability.
It wouldn't be as obvious as,
No. So somebody did that back in like 2005, I think. Somebody owned one of the Linux kernel developers and changed an if statement to, instead of equals, they just changed it to equals. So it was like your UID, it was a check against the UID, and if your UID was 0, do this, and he changed it to UID equals 0. You know, it's like, whatever. Off track. Good comment though. So the reason I show this is I want you guys to now start thinking a little bit more about like how we could exploit this. So client versus server, hosted versus shared environments, grid computing environments. At what point is an interpreted language getting executed, and could a vulnerability in the interpreter allow me access to a lot more than what I should have? So with these distributed environments that have these interpreters within them, you might be able to break out of sandboxes. And if you're able to break out of this sandbox, you have access to every single App Engine application, right? So Google's not unique. Amazon's doing the same type of stuff, and a whole bunch of other people are. So because of that, there will be more bugs. So, all right, easy target. PHP. So yeah, some people say PHP is like just giving a little kid a big gun. PHP is an interesting language as far as it has a low barrier to entry. It's a language that mixes markup and functional language all in one, very much like classic ASP did. Me personally, I started coding PHP in 2000, let's say, and it was my first web app language, and I was thrilled that I didn't really have to know much, and everything I wanted was just there. Like I would make up functions, and they were already existed. Sometimes I would put underscores, sometimes I didn't. Both of them existed. There were aliases for each other. So that is, some might say, one of the problems. Like PHP just has billions of built-in functions, and as far as the language itself, it has so much functionality that the attack surface is huge. In 2007, I believe, Stefan Esser, who is one of the... Actually, let me just speak a little bit about Stefan Esser. So Stefan Esser is my hero bug finder. He was one of the PHP core security team, and he was actually the PHP core security team. What he did was he constantly audited the PHP core code base, looking for internal language vulnerabilities in the extensions, and every variation of things that he could find. And he was very, very good at this, and he found lots and lots of bugs. So there's hundreds of bugs accredited to him being fixed in PHP. But at some point, the PHP core dev team became a little slow to acknowledge his work. And as with a lot of security work that we do, people just get desensitized to the fact that you're finding remotely exploitable buffer overflows every month. Right? And then they're just like, well, the last 6 we fixed, nobody really worried about, and we didn't get screwed in the public for it. So we're just going to put in this optimization fix before the security fix. And this is just the psychology of SDLCs, right? So people get desensitized, and it gets slow to roll in fixes into your main line. So Stefan got frustrated with this, and then he left the PHP core security team, and he started the month of PHP bugs. So, or life of PHP bugs if you followed PHP for the existence of its history. So what he wanted to do here was he had a whole cache of all these vulnerabilities in PHP. And he tried to give them to the PHP core dev team, and they just sat on them. So he said, all right, public, here you go. And he, once a day for an entire month, he released a bug in it. And he actually had so many bugs that he went past a month, and he released 41 in total. So, yeah, he has 41 vulnerabilities, and 22 of these were previously fixed. There's the numbers. But the most important number here that I want to point out is the one on the bottom. Number of month of PHP bugs not fixed, 5. And that's current. So why would PHP not fix these vulnerabilities? Anyone know? Does anyone keep up with this stuff? No? All right. These 5 vulnerabilities were in parts of the architecture of the PHP engine that were central to how third-party plugins fit into it. Now, if you know PHP, you know that there's a company called Zend that produces PHP. And what is Zend in the business of? Making third-party PHP plugins. So it is not in the best business interest, I would think, for Zend to make changes to the architecture of PHP that breaks all their products. So you have a little bit of commercial stuff coming in with open source stuff. Where they meet, security takes a hit, right? So I trolled a lot of blogs and stuff and read some inside info about people speculating and saying that this is why. So this is not my source. The internet told me, so we believe the internet, right? But I mean, it makes sense when you think about these 5 bugs and you look at them and what parts of PHP they were. They were in parts that would break third-party apps. So the parts would break the architecture, but not necessarily would change the way that applications are interpreted or anything like that. PHP itself would continue to work just like it would have, but it was the core engine that would have had to been changed. So in the month of PHP bugs, where were these bugs found? Going back, if you think back to that process diagram I showed at the beginning, 4 were found in extension library functionality. So 15 were found within the internal virtual machine, and 22 were found with problems having to do with the native functions. So PHP has a ton of built-in functions, and some of them you give malformed input to and they'll break, right? So the internal VM ones, those are pretty bad, especially for the hosted environment solution, or the problem I was talking about before. So if a hosted environment is not running PHP in the right PHP exec with SureOcean and safe mode enabled and every possible thing that they could have, if they're not thinking of security as number 1, then they're going to have a way to be exploited by a bug in the internal VM. But where were bugs not found in PHP? So he found no bugs in the parsers and no bugs in the bytecode interpreter or the virtual machine itself. So you can give straight bytecode straight to the PHP engine, and it'll accept that. It'll skip the interpreting step and the parsing step, and it'll go straight to the interpreting step at the virtual machine. So we can kind of shortcut that whole process. We don't have to go through the whole loop. We can just go whoop, right here and see if there's bugs there. So with PHP, given its history, thousands of bugs, I think we're done. There'll never be another vulnerability in PHP. So nothing to worry about there. All right, so Stefan Esser found lots of bugs in the interpreter. So that's like a pond that's been fished. There's still bugs there, and because they're actively working on code, there will be more bugs introduced. But it's kind of been heavily fished, as well as the external libraries. He's found lots of bugs in that. It's also heavily fished. So we have all these points right here, right? So malformed PHP syntax. What if my keyword is too long? What if I have a function that's just named way too long? A funny bug I found back in the day was there's this patch to the GCC compiler called ProPolice. And basically, if you had a source code, I just had a main, and then I called function foo, but instead of foo, I named it 50,000 A's. So ProPolice used to choke and had a heap overflow on if you had a function that was too large, the function name itself. So just simply the security patch for GCC had a buffer overflow in it. But this was back in like 04, 05 maybe. But it's way since been fixed. So, but this is the type of things that I'm talking about, right? So what if the syntax and the semantics? What if I have like 10,000 curly braces matching up with 10,000 curly braces? It's all perfectly legitimate as far as the rules of the language go, but am I overflowing a recursive buffer that it's copying? What could I possibly be doing at the semantic level even? So if I have a recursion in some way that just shouldn't work in my language, like I have a class calling a class, and with the instantiation of that class, I go back to the instantiator of the other class, right? So the semantics of the language, you could have bugs there. And all of these things try and trick the parsers and the interpreters and the intermediate language points into just getting into unexpected states. When you get into unexpected states, things break, and oftentimes those are exploitable. Yeah?
Yeah, I was just thinking about that. I saw where you had the libp3 overflow with the quantifier, but wasn't there another one where if you nested sub-expressions, say you just did a bunch of left parens and put like a star inside, and there was an overflow by
Yeah, exactly. So Derek, is it? So Derek mentioned another bug in PCRE where you just had a bunch of left parens and then you used the star wildcard character, and it just choked on that because it builds up one internal buffer within its parsing engine, and then it switches to a different state. And on that context switch to a different state, it didn't copy the buffers right. And there's all sorts of bugs like these that I love, and people are not finding many of. So the next language we'll talk about, and please, if you have anything to say, just jump in. So the next language is JavaScript. So JavaScript, out of all these languages that we're talking about, JavaScript's probably the one that has had the most publicized bugs within them as an interpreted language, right? So there's tons of JavaScript fuzzers out there. HG's got one, my mom's got one, Michal Zalewski made one, and a bunch of people have made JavaScript fuzzers. As well as HTML fuzzers. Those have been popular as well. And I mean, the point of that is we're trying to find client-side bugs in the most popular client there is, the web browser. And Mozilla saw this stuff and they said, hey, everyone's finding these JavaScript bugs. We should write a fuzzer to find these bugs as well. But whereas the HDM and the Michal fuzzers, they were concerned more on the function level, right? So let's say the DOM functions, or, document.location, what if I gave it a location that was 20,000 A's, right? Or does it crash? What if I gave it a location that was %n? So that's what these fuzzers were working on. They're primarily trying to find bugs in the DOM functions, right? So what if I call document location and then I call another function that switches my location, and at the same time there's a race condition, and so they're trying to find race conditions and buffer overflows and format string bugs within all the DOM functions. So what Jesse Ruderman from Mozilla did was he made something called JS Fuzz Fun, and his fuzzer is a little different. His fuzzer actually makes JavaScript code that tries to break the interpreter, right? So he focuses a little more on the syntax level, and I was really happy to see that was the first big fuzzer out there that focused on that. Now, as far as I know, JS FuzzFun, nobody's extended it to work with other browsers besides Mozilla-based ones. So it has a little bit of Mozilla-specific stuff in there, but it wouldn't take you a weekend to just chop that stuff out and run it on IE and Opera and what have you. But what, besides browsers, handle JavaScript? Open question. From the back? Adobe Reader, yeah. So there will be more bugs. So in the past year, we've seen a ton of JavaScript bugs in Adobe Acrobat Reader. And I have some, before I was ambivalent towards Adobe, I was like, they're just like any other vendor. But I have some personal recent experience where now I hate them. So when this most recent JBig 2 bug came out, the one that they just released a patch for March 11th, I said, okay, I'm trying to protect the people I work with, right? How can I stop this bug? So I read the deployment documentation for Adobe Acrobat, and it says, hey, if you want to disable JavaScript, you set this registry key, disable JavaScript. I was like, oh, wonderful, just set this registry key. So I go and I set the registry key and blah, blah, blah. 3 days later, I'm just like, hey, I wonder, yeah, I started researching the JBig 2 bug on Foxit Reader, right? And I started writing JavaScript PDFs. And I was like, hey, I wonder, just out of curiosity, this one weird JavaScript PDF that I'm running in Foxit Reader, what's it going to happen when I open it in Adobe Reader when I have JavaScript disabled, right? So I go and I open it in Adobe Reader, and it pops up, says, there is content in this that you have to run, yes or no? And I was like, what? What is this? Is this because I like made a weird JavaScript? So then I just took some PDF with JavaScript. It was called calc.pdf. It was just an example of how to make a calculator in PDF. I opened that up in Reader and saw the exact same thing. So when you disable JavaScript in Adobe Reader, it doesn't disable JavaScript. It just prompts the user, would you like to run this, yes or no? That's why I hate Adobe. So yeah, like iscincidents.org, like all the blogs out there, everyone was just like, set this registry key and you're safe. All your users are safe. As we know, that's wrong for 2 reasons. 1, the JBig 2 vulnerability can be exploited without JavaScript, and 2, doesn't actually disable JavaScript. So I started working on a binary patch for this because I'm just, it's a very simple thing. I just actually started working on it like 2 days ago. Just process stalking, opening a normal PDF versus opening a JavaScript PDF, and just trying to find where it branches and just trying to knock out, never ever go and open the JavaScript. So I may release that at some point, but it was more for my purposes. We'll see. So next language we'll talk about is SQL. So SQL, I've got an excerpt from an article by a guy named Raheel Ahmed. He's a developer, and he wrote this on some website called easyinarticles.com. And he was talking about SQL injections and problems with SQL when you're dealing with web application development, right? So he makes 4 points, 4 problems in SQL security. He talks about, and primarily with SQL injection. He talks about SQL manipulation, right? So that's when you either modify the existing SQL or can append more SQL. He talks about code injection. That's when you can append more statements instead of editing the existing statement. And then he talks about what he calls a function call injection. And that is basically an advanced variation of the previous 2. It's like, let's say you can call XP command shell, right? And then finally, he talks about buffer overflow. So I'll just read it. Buffer overflow is caused by using function call injection. For most of the commercial and open source databases, patches are available. This type of attack is possible when the server is unpatched. So, we know in security that that's not true, right? So there are things as 0 days. So you can call a function, and in this context, he means a native SQL function or a stored procedure or an extended procedure. Depending on your RDBMS, they may call them different things. Like in MySQL, they also have user-defined functions and things of that nature. So we'll just call all these things functions, right? And these functions in SQL have problems with them. And you'll find memory corruption issues as well as parsing issues and things of that nature. So I think he was getting on the right track here, but he didn't really, as a developer that doesn't focus on security full time, he didn't really see like the big picture. The big picture is you can exploit buffer overflows through function calls that you can take over through a SQL injection, right? So now my SQL injection, instead of just getting on the database and pulling out everything from the current database, let's say I have an associated database that's just this application. Let's say I do a SQL injection that exploits a buffer overflow in xp_send_mail, which is stored proc in SQL Server. And now I exploit that buffer overflow. Now I'm in that SQL Server as the process that the SQL Server is running as, which I think is network service now. So now I'm a network service on the SQL Server box itself. So now I have data access to a whole lot more than just the 1 DB I was on. And any views or any access control layers or any of that, all gone, right? Because you are the SQL process. So bugs in a SQL interpreter will let you accomplish these things. Not just bugs in the function, but bugs in the syntax and everywhere else that I've mentioned. So why did I even come up with this whole thing? Why did I even start researching this stuff? Is because I was thinking of this SQL injection as a remote code execution problem because I was writing this exploit. So this is sewomantech.pl. It's a remote exploit for the Symantec reporting server. This is I've never released this. This is ODay code, whatever. But it's totally useless. And here's why. Because it executes arbitrary PHP code on an IIS server that is set to be totally locked down, on a PHP engine that is set to be totally locked down, with a SQL Server 2005 backend that is totally locked down, right? So what you'll see here, some of the things I tried to execute, system calls, pass-throughs, includes, execs, everything failed because it's just set up to be totally locked down by default. So I was thinking, all right, well, I can execute arbitrary code, and here's the, where is it? Somewhere down. Okay, so here's the best part. It's pre-auth, right? So the bug is in the login page. So it's remote command exec, and you can just execute whatever PHP code you want. So great, I'm executing PHP code, but what does that give me? I want to eventually execute system commands, right? So I couldn't get any system commands to run, so I thought, all right, what's the next level I want to get? I want to get on that SQL server that not only usually holds the reporting data, but usually holds all the update data for semantic antivirus. So if I can start playing around with the semantic antivirus update database, well, that means something. Now I could push a bad update to every semantic client or something, So I started thinking about these SQL bugs as an interpreted language problem because I can get PHP code to execute, which means I have access to the username and password for the SQL server, which means I can do arbitrary SQL to the SQL server. But I want to use that to elevate my privileges, right? So I started thinking about SQL parsers and writing fuzzers for SQL and things like that. And I found out that nobody's looked into this, right? Nobody's made a SQL fuzzer. Nobody's even thought about it. And I'm looking at this in a little different context. So first we started talking about interpreted language bugs as a hosted server problem. Now we're talking about a server-side problem. And next I'll show you how it can be a client-side problem as well. So where do the bugs live? So I spoke about the functions, right? Microsoft Jet Database Engine, which is also known to most folks as Access Database, or those .mbd files. So if you can get a SQL injection into Access, you could call one of the functions, and there was an overflow in that, and now you're executing code on the server in the context of whatever the Jet Database Engine is running in. And at the semantic level, you can put different things to fuzz that, syntax level, etc. And Brett Moore, in his paper Access Through Access, at the last line in the paper, it's just as an afterthought, he kind of mentions, hey, oh yeah, you can also exploit buffer overflows and access through SQL injection. It's just he doesn't the whole other 20 pages of the paper is talking about different SQL injection techniques, but I think there's a lot more interesting things in exploiting memory corruption through interpreted language vulnerabilities. And also at the database kernel level. So every RDBMS has native primitive types, just like Ruby and Python and all these other guys. There might be bugs at that level as well. So is this only a server-side problem? So Firefox, as of version 3 series, ships with SQLite 3.5.4.1. And SQLite, for those that don't know, is a lightweight SQL database engine, right? So it has the basic SQL support, but it doesn't have any crazy things like stored procedures or triggers or anything like that. It's just basic SQL, the most basic SQL syntax that you need to be SQL compliant, or not, whatever, the standard, SQL standard. So in SQLite version 3.4.0, they got really lucky. If you look at their changelog for 3.4.0, there's a bug reported on it, and it said, just some guy from the internet, not a researcher, not somebody that knew what they were doing, just said, hey, I heard sprintf and strcpy are bad. I think you should take them out of your code. So the developer, usually you have developers and they have these pissed off, like, I'm better than thou attitude, and they're like, no, it's fine, my code's good. But this guy actually did a really cool thing. And instead of like shutting this guy down and denying him, he said, all right, you got a point. I'll change every single sprintf and every single strcpy. And in the 3.4.0, he changed them all to snprintf and or strncopy. And just that one action by some random guy on the internet reporting this and it getting fixed, he fixed dozens of buffer overflows. He got so lucky. He didn't even realize it. So that was all fixed in June of 2007, around the same time that Firefox put it into its mainline. So there would have been a crap load of buffer overflows in SQLite, but now they're a little better. They're still there, but there's not as many as obvious ones. So SQLite does have 50 native functions. And if you write a very simple fuzzer, it's very, very simple. You just throw the data that it expects at the types that it expects, and they'll break. It's pretty simple. And talking about that forking problem that I mentioned before, where like people fork. Oh no, I didn't mention the forking problem, actually. Let me mention the forking problem. People will fork open source code projects and then bring them into their tree. And then they will forget to take the upstream patches. So it's not just using an open source project, but it's fully forking it and bringing it into your product. And WebKit, which is again the HTML and JavaScript engine for things like Safari and Chrome, WebKit tends to do this a lot. They did it with PCRE, and they also did it with SQLite. So they just fork off their own version, and then they rewrite a ton of it to be very specific to them and optimize a lot of it for their environment. So now it becomes a client-side problem. So now I can own Firefox through a SQL interpreted language bug. Like, how weird is that? How weird is the fact that there even is a SQL interpreter in Firefox? Like, why would anyone have that? Anyone? Bookmarks? True. So Firefox started using SQLite databases for their bookmarks and other internal data stores. But they could still do that without giving like the JavaScript client access, right, to SQL. They could just put it in their own internal libraries. The reason that they actually have it accessible from JavaScript is for HTML5. HTML5 means job security for us in the insecurity industry. HTML5 says you have to have persistent client data storage, and it has to be a SQL database. And if you read section 5.10.2 on database storage, it has all these crazy requirements. Like you have to embed an RDBMS into your browser. Like, who thought that was a good idea? So, Alberto wrote this paper on abusing HTML5, and one of the things he talks about is this database storage.